All right, welcome back. Let me go ahead and continue from where I left off. So, we were talking about inertia, or Newton's first law, okay? And I just want this to kind of show you guys what or why we need to know about physics, I guess, in general, okay? Because a lot of times we kind of get stuck in the math, okay? And we kind of forget of, wait a minute, why are we doing this? Okay. And I understand that because it's happened to me before too. Okay. So when we're looking at Newton's first law, the reason it's so important is because it has to do with our daily lives. Okay. So here's an example. So we have a little giraffe driving, which first of all, pretty sure is illegal, but I don't know. Okay. And he has a little seatbelt on, okay, as you can see. So as this guy travels this way, okay, he travels and he hits some wall, okay. His car suddenly stops as he gets to that wall, but his body keeps moving, okay. So that is Newton's first law in action, okay. An object at rest stays at rest. Object in motion stays in motion, okay, unless acted upon by another force. So this guy is moving the same speed as the car, okay, so with the same, traveling at the same speed, okay, and suddenly hits a wall. That body, or the giraffe, will keep moving at that speed, okay. If we have a seatbelt on though, that seatbelt will stop you from keep going that same speed. Okay, so it'll hold you back with the car. So that's why it's so important to wear a seatbelt. Okay, we need to wear a seatbelt because we don't want to, lunge out of the car. Okay, once we hit a wall, which hopefully you shouldn't hit a wall, but besides the point. Okay, so this is why we need to know physics, why we need to understand physics. Again, we get really caught up in the equations, the math, but it is day-to-day stuff that we need to understand, okay, or we wouldn't have seatbelts that were invented, and bad things would happen, okay. So moving on to Newton's second law of motion. Let me do something real quick. Okay, so Newton's second law of motion kind of relates what the first law was trying to talk about. Okay, so we know that the force of an object, okay, is somehow related to mass and an acceleration. Okay, so what I wrote here is force is proportional. That's what this little sign says. Proportional. If I could spell, that would be great. I didn't go to college for English, all right? Bear with me. Okay, proportional to mass and acceleration. So we need to somehow come up with a formula that has force being proportional to mass and acceleration. And that's exactly what Newton did. Okay, he came up with this formula here. Force equals mass times acceleration. Okay, so our net force, okay, of an object is the product of its mass and acceleration. Okay, and I wanted to quickly mention the units of force. Okay, the units of force, that is in newtons. Okay, so that's that big N there. And 1 Newton equals 1 kilogram times mass over second squared. Okay, and you can kind of remember this. This is how I remember units a lot of times. I remember the formula. Okay, so force, right, is in newtons, I just said, and mass is in kilograms, acceleration is in meters per second squared. Okay, so that's all this says. Whoops. Okay, I just wanted to quickly mention that just in case we have to do any kind of unit conversions and such, but just to get you guys going with the idea. Okay. So I wanted to also mention the definition of acceleration. Now we have talked about acceleration, and we know that it's some kind of change in velocity, okay, which is also just the change in motion. So again, remember in the first law of Newton's laws, okay, his first law said a body in motion stays in motion, body at rest stays at rest, okay, unless it's acted upon. Now, when it's acted upon, there is going to be some change in motion, okay? So that change in motion is actually your acceleration, okay? And I wanted to mention what an external force is. Okay, so that's anything that is outside of the system that is acting on that system. Okay, so my system could be a person, it could be a ball, it could be a box, okay? And my external force could be, you know, a hand pushing on that ball or somebody pushing on that person and so forth. Okay, that would be my external force. Or even gravity. Okay, that would be an external force. Friction, okay? So all of these are external forces. And I did write a note here that you want to define boundaries of the system before you can determine what is external. So again, I said if you have a ball or if you have a person, box, whatever it may be, okay? So just make sure that you know kind of what you're looking at in the system, okay, before just starting to define things. Okay? Okay. So I wanted to go over friction. Okay, this is an important concept that we will be seeing. Okay, so friction is any kind of resistance to movement. Okay, so it's a force that resists the relative motion of an object. Okay, so this is an example here of say a table, and this is a book on the table, and when you try to just slide a book on a table, it kind of resists at first, right? If you just start slowly pushing on it, just like with a little bit of force, it's like, oh, I can't really overcome that yet. But with enough force, you can start moving that book along, right? Okay, so that's an example of friction, and that one's actually static friction. Okay, so static friction is that initial friction when trying to move an object, okay? So from rest, or it's static, okay? We also have sliding friction, which would be like ice skating, like in the very first example I told you guys about, but we were neglecting friction. Rolling friction would be like bowling. Fluid friction, which could be air, water, any kind of liquid, okay, any kind of resistance, okay? All right, so going back to Newton's second law of motion, we have this equation, right? F, force equals mass times acceleration. So F equals ma. Okay, now if we wanted to do a quick example of that, okay, so I have F equals mass times acceleration. Okay, and I'm looking at this situation. Okay, I have two rocks, rock 1, rock 2, and they're both just falling from the sky. Okay, say that they were just dropped. Okay, and we have looked at motion just before. We've looked at projectile motion, free fall. Okay, so now we're going to look at those forces behind these motions. Okay. So this first one, I see that this has a 10 kilogram mass. Okay, so my mass here is 10 kilograms. And I have a force of 98 newtons. Okay, so this is our force. And this subscript right here, grav, means gravity. Okay, so this is our force due to gravity. Okay. Okay, so that is always the first thing that I like to do when I'm looking at a problem. I kind of just look at what I know, okay? Then I can look at my question. So my question is, what is the acceleration of the 10 kilogram rock? Okay, now I have my equation, force equals mass times acceleration. okay? I have force and I have mass, and I want to know acceleration. So I can use this formula just by a bit of rearranging to find that acceleration, okay? So what I'll do is I'll take my equation, F equals ma, and I will solve for acceleration. So I'll divide by mass on both sides, and I get acceleration equals force divided by mass, okay? So I'll plug in my numbers. My force is 98 newtons, and my mass is 10 kilograms, okay? So I can do that on my calculator. 998 divided by 10 is going to be 9.8. Okay, and let's look at the units for a second there. So going over here real quick, I have newtons over kilograms. So remember, my newtons is going to be kilograms times mass, I'm sorry, meters, not mass, meters per second squared. Okay, so that's my newtons. And again, divided by my kilograms. So my kilograms cross out, and I'm left with meters per second squared. Okay, so that is my units here, which makes sense because that is the units of acceleration. Okay. All right, so my acceleration on this first rock is 9.8 meters per second squared. Okay. Now, I want to do the exact same thing for my other rock here. I am looking for my acceleration of the 1 kilogram rock. So I'm going to take my same equation, A equals F over M, and plug in my numbers. So I have my F gravity as 9.8 newtons, and my mass as 1 kilogram. And 9.8 divided by 1, of course, is 9.8. And we had the same units, so we're going to end up with meters per second squared. Okay? All right, so as you can see, we got the same answer. Okay, and now the importance of that is that our acceleration due to gravity is universal. Okay, it's same around Earth. Okay, no matter how big the object is, how small it is, we still have that same acceleration due to gravity. Okay. All right, let's see what is next. I will actually stop the video here and continue in the next video. All right.